Okay, so you fit some regression model. What are you going to do with it? Let's talk about some different ways you can interpret these models and make use of them. So first, just in a purely descriptive sense, this is actually maybe the most kind of common way that people are thought, but honestly, it's probably the most useless way, and we'll see why. So you have these coefficients, right? And these coefficients, in some sense, are the slope of your prediction function. And so this one coefficient tells you how much your prediction increases if you fix all other predictors and increase just this one by a single unit. So to see that, let's just say that we can write mu hat, let's say for two predictors, x1 and x2. So your function is beta 0 plus beta 1 x1 plus beta 2 x2, right? So how can we interpret, for example, this beta 1? Well, if we fix x2 and we increase, we can, let's say, what is the value of the prediction at if we put x1 plus 1? So we increase x1 by 1 unit, and we fix x2 at the same value. How does our prediction change? Let's compare these two. That's going to be beta 0 plus beta 1 x1 plus 1 plus beta 2 x. So if we take the difference, this from that, it's subtracting these two. So that's going to cancel with that. These two terms cancel. Here we have a beta 1x, and here we have a beta 1x. And then what's left over is this 1 times beta 1, which is just the beta 1. So beta 1 is equal to exactly this difference in, this is a minus, so, well, you could do that minus that the same way. So it's the difference in the predictions if I increase this one predictor corresponding to whatever beta we're talking about, but I leave all the other ones fixed, right? That's the very common interpretation of these coefficients. And if you want to kind of see that like geometrically, so you can imagine that this is your prediction surface. So when you have a multivariate prediction, you're going to get a prediction surface that looks like this. So here's y, and here's x1, and here's x2. So however much this is increasing in the kind of x2 direction, that slope is x1 direction is beta 1, and however much this is increasing kind of in the x2 direction, that's beta 2. So these slopes are indicative of how much this prediction surface is changing as we move in each direction. So this is all true. This is a fact, right? It's just descriptive of this prediction function. So why is that maybe not that useful? Well, it's just descriptive of the prediction. So it's my mu hat. This is really not telling us anything about the actual conditional mean because we don't know what that is. And as we discussed previously, the actual conditional mean function probably is not linear. And so these coefficients don't actually have any real meaning in the actual world itself. So, okay, that begs the question then, why would you care about how much my prediction increases if I fix all predictors and increase this one by just a single unit, if it's really only a statement about the prediction function itself that you got and not anything in the real world? So let's kind of dig into that a little bit. Let's look at an example here and show you how maybe the intuitive interpretation that you might have from this, it doesn't really hold up statistically in many cases. So let's say we have this data set here that I'm inventing. This data set, let's say these are defenders who are playing football, and I'm measuring the height and the weight of these players and some measurement of how many tackles or how successful their tackles are. And so what you might expect intuitively, if you've ever seen football, is that these dudes are big And the taller they are and the heavier they are, the more successful they will be at tackling these players. So I would think that, okay, if I increase a player's height and I hold everything else constant, that should increase the amount of tackles that they're getting. And in this example, or same with weight. In this example, the way that I'm actually making this data generating process is so that is indeed the case. So here I'm setting their height and then I'm setting their weight, which in this case depends on their height. That makes sense. Taller people are heavier generally. And then I'm setting the tackles to be given by this linear combination of height and weight. And you see both of those have positive coefficients, 1/6 and 1/over 200, plus some random noise. So here I'm cooking up the data. This is simulation. It's fake. In reality, we could never see this. But I'm cooking it up in a way that there actually is a linear relationship, and the coefficients are both positive to kind of align with your intuition. So let's see what happens if I draw some data from this data generating process and I actually run linear regression. What do I get? So I put in tackles as the thing to be predicted, and then height and weight as the predictors. I use this defenders data, and you can see what I get is actually a huge negative coefficient on height, and a largish positive coefficient on weight. So one thing to notice immediately is that these things are on different scales because these predictors are on different scales. So here weight is roughly in pounds. So I have this so that for a person who's 6 feet tall, their weight on average will be 200 pounds, and height is in feet. So already you can see, the scales of these things are not really comparable. So that's something to note, and that's always the case. Another thing is that, okay, this thing is, I'm getting negative values for height. That does not align with your intuition, right? If you were to just kind of naively look at this and say, okay, well, taller players, then holding everything else constant, taller players should get fewer tackles. That would seem surprising to you, right? But that's actually not surprising at all in this example, and we'll talk more about that next week. But the problem here is that there's no quantification of uncertainty. So if I had some quantification of uncertainty on this coefficient, I would see that there's actually a lot of uncertainty for both of these. And so it very well could be that the effect here is this coefficient is positive, and this one should also be positive, but it's really hard to tell based on these data. That's what that would tell us. So we'll see more about that later. But more fundamentally, the other issue is that it really depends, these coefficients, what they come out as really depends on what else is in the model. And that's because if you put in here tackles versus height and weight, what you're estimating is some linear approximation of the conditional mean of y given x1 and x2. If you keep out weight, then it's a conditional expectation of tackles given just height. And similarly, here we have tackles given, conditional expectation of tackles given just weight. And these are just different functions. There's not necessarily a relationship between them or assumptions that we can make that relate them. They're just different linear approximations. And if you leave something out, the best linear approximation without that thing is not necessarily related to the best linear approximation when you put that in. So let me hopefully try to explain that a little bit better. So this one here, if I'm interpreting this coefficient here, right, as like, okay, this is what how much my measurement of tackles increases if I fix weight and I let height increase by 1 unit, then I should see tackles decrease by 217 units, right? So how do I interpret this one here, right? Because here now weight is no longer in the model, so I'm no longer holding that fixed. So this one I can interpret as if I increase height and then I let weight do whatever it wants. So weight is now being drawn. It's not being fixed, but it's now being drawn essentially from the conditional distribution of weight given height plus 1 or something like that. So now weight is allowed to vary. And so I need to interpret this coefficient understanding that this is not holding weight fixed, right? Or this is not holding any. Consequently, if I look at this one up here, the thing that you need to remember is that here, yeah, weight is being held fixed, but everything else, anything else that I'm not measuring is allowed to vary in whatever way that it wants. And what that means is that my coefficient on height is kind of sucking in whatever. It's trying to explain the tackles the best it can, right? Maybe there's some other stuff. In this case, I cooked up the data, so I know there isn't. But maybe there's some other stuff out here that I'm not including in the model. And if I did, it would help explain tackles to some extent. But it's also correlated with height. Well, since I'm not putting that in, whatever explanatory effect of those variables is being taken up by the height in this case. So here, for example, you can see that because here I'm leaving weight out and height is kind of doing the lifting for weight because these things are actually very similar to each other. Height and weight, somebody who's very tall is also going to be very heavy, right? And so what this is telling you is that the model actually doesn't need both height and weight, or I mean, it can maybe it's fine with both of them. But all the model is trying to do is predict, right? It's just trying to minimize the mean squared error. And what this is telling you is that okay, if I just have height, then I can predict pretty well, and I could compare the MSEs of these and show you that. But here height is positive because it's telling you that taller people do more tackles. Here weight is positive because it's heavier people are doing more tackles. And here this one is negative because it's saying, okay, yeah, heavier people do more tackles. The height doesn't matter, basically. Yeah, it's a negative coefficient, but if you put the predictions together, you're going to get the same kind of predictions with this model as you are with this model. Maybe this one's and these two are doing a little bit worse, but they're basically the same. And so the point here is that this is not surprising or wrong. We'll dig more into this in the next lecture to kind of give you, right now, since you don't have an idea of like kind of the sampling variability of these things, that some of these concepts may not be as clear. But the point of this is that these different coefficients, having something in the model or not in the model, you're estimating different functions because these are different conditional means when you condition on different things or don't condition on different things. And so these are answering this coefficient, even though it looks like it's the same coefficient, right? This is the coefficient on height, this is the coefficient on height. But no, those are fundamentally different things. If you add something in the model, those are not interpretable the same way. You can't have, there's no apples to apples comparison between those. So they're really answering fundamentally different questions because they're describing different prediction functions, okay? And moreover, I would say neither of these have good real-world interpretations unless you're willing to make further assumptions, because like we saw here, this is really just descriptive of the prediction function itself, not of the true conditional mean, which is probably nonlinear in the first place. So hopefully that should kind of give you an idea of, like, you can look at linear regression coefficients and try to interpret them descriptively, but really it's just a description. What you're describing is just the prediction function, and beyond that, it's just vibes. So you can maybe use that to generate hypotheses and then go do some things that are more careful. But beyond that, you can't look at this and say, oh, okay, yeah, if I somehow gave football players bigger shoes that would make them taller, that would make them be worse at tackling. That is actually a causal interpretation. We'll talk about that shortly, but cannot be done just by looking at this without making further assumptions. So let's do a little problem here. So let's download this data set. We're going to do some regressions and then look at the coefficients. Okay. So we'd like to regress total charges onto age. Okay, so here the coefficient we get is 257. And now we want to add BMI and smoker variables. Now look at it. Okay, so in this case, it's actually super similar, right? So that's interesting. So however, they are slightly different. And the question is which of them is correct? Which of them should you report or say something about? And the answer is that they're both correct. They're both correct. They're just correct for different questions, right? So this one is if you want to know what's the conditional mean of charges given age, then this is the slope. But if you want to know what's the conditional mean of charges given age, BMI, and smoker, and smoker, then this is the slope. So neither of them is right or wrong. They're just fundamentally different questions. And maybe, I don't know, let's see, what about BMI? So BMI also in this example, so this one changes a little bit more drastically, you can see, by adding these other variables. So the point of this is to show you, okay, there's some examples where adding more stuff is going to change it. It can decrease, it can increase. There's really not a solid way to know which way it's going to go, and it's not good or bad either way. It's just different. Okay, it's fundamental limitations of trying to use regression models in this way.